Hello, hello guys, how are you? This is Algorithms or Engineer, the Alt Engineer from YouTube. Today we're going to talk about the first lecture, Introduction to Digital Logic Design. It's the first time for me checking this lecture too for Waveform Representation. And it's done by Haiju, sorry for mispronouncing your name. And it is the course EECS 303, Advanced Digital Design Fall 2011. So sorry for taking this really old PowerPoint, but I'm still not started school at all, but I'm trying to get ahead with my courses so I can have an idea what I'm doing. So as I said before, this is the first time for me checking this platform. At the moment, if you might heard any background noises, it's because I'm in college dorm. And it is really noisy here. I thought it'd be more quiet, but what can I do? Sorry about that. So the outline will be the class administration, digital design, to read in chapter 1 and 2. You don't need this one, but if you want to take a look, this is the book by Mano and Kim, Logic and Design Fundamentals by Prentice Hall. Class note, there are copies of lecture and transparencies has to be available. So do you want me to... Okay, I still haven't found a shortcut for this one, sorry. Let me see. So okay, the process of design. If you have heard of me from the last course of computer science fundamentals, we have talked about design of the data structure and how it is implemented and how we use it. And in this case, we're going to take the process of design of digital logics. The initial set is what is a function performed by the object. Constraints is how fast, how much area, how much cost, and we have to refine the abstract functional blocks into more concrete realizations. Now, sorry about that. How much it costs, refine abstract functional blocks into more concrete realization. How fast, it only depends by the CPU components, how much area by the motherboard, and how much costs. You can use the greedy algorithms. We have learned Bellman-Ford and Jocasta algorithms. We have to refine the abstract functional blocks into more concrete realization. Okay. Let's begin with limitation. We have to assemble primitives into more complex building blocks, and the composition via wiring. We have to choose among alternatives to improve design. Debug. We have the faulty systems, design flows, composition flows, component flows, designed to make debugging easier, and hypothesis formation and troubleshooting skills. This is a digital system, digital versus analog waveforms. Yes, this is more easier. 1, 0, and directly with only subdiscrete values, while in the waveform you can show the 1 up, 0 down, up, and 0 down. On the analog side, the values vary over the broad range continuously. As you can see here, we have some continuous form, but it only say 1, 0, 1. This is the same, okay? But it only depends on how much easier it is for you. Sorry if I miss say something else, because it's the first time for me checking this PowerPoint and checking this course, so I'm trying to prepare and go ahead for it. This is Boolean algebra, logical operators, algebra, variables, values, operations in Boolean algebra. In Boolean algebra we have true and false there. I forgot. The values are the symbols 0 and 1. Okay, I'm pretty sure that these lasers are really noisy. The values are the symbols 0 and 1. If a logic statement is false, it has value 0. If a logic statement is true, then it is value 1. We have a method truth table there, operation and or not. If you remember from my first course of digital logic, we have seen the design of this logic gates AND with a straight, or if it's curvy or not, it's the inverse of it, and curvy too. Okay. Then we have exclusive OR and exclusive NOR, NAND, NOR, etc. So let's check this one. We have X and Y, because 0 and 0 got 0, 0, 1 give us 0, 1, 0, 0, 1, and 1 give us 1. If you remember on the end, logic gates means that if the both components have to be on, it means the output would be on, means 1. If at least 1 is 0, it cannot be on. While on OR it is different. You only need 1 on. For example, let's check the truth table: 0, 0, 0, 0, 1, we have 1, 1, 0, 1, 1, 1, 1. And the not, of course, not is the inverse of it. With this, I said, with a bubble head. I don't know this called because I don't officially a not in college. Okay, sorry about that. But I'm gonna call it bubble for now until I find something else which is more suitable for it. 0, 1, 1, 0. We have combinational versus sequential logic. X1 an input and xn to the xn input. We have a switch network. Oh, nice. We have a Z1 input, Z2 input, Zm input. The network implemented from the switching elements or logic gates. The present of feedback distinguishes between the sequential and combination networks. The combinational logic has no feedback among inputs and outputs. Outputs are pure function of the inputs. For example, we have full adder circuits. We have A and B, which is carry in the mapped into the sum carry out. Count. Oh shit. If you remember, if you are familiar with C and C++, we have code to print something which has been carried out. You know? The more you grow, while you grow, more you learn. So we have a sequential logic and inputs and outputs with overlap. Outputs depend on inputs and the entire history of execution. The network typically has only a limited number of unique configurations that are called states. For example, traffic light controller sequences infinitely through 4 states. New component is sequential logic network. Storage elements remember the current state. The output, the new state, is a function of the inputs and of the old state. For instance, the feedback inputs are the state. I didn't quite get that, but output, the new state, is a function of the input of the state. Okay, no problem. A synchronous system, period reference signal the clock causes the storage elements to accept new values and to change state. And we have asynchronous systems, no syndication when to change state. I see. With asynchronous, it changes states and this causes the storage to accept new values, okay? Where the asynchronous, there is no signal to change state. So there is a case study of a civil logic design, 7-segment display from L1 to L246 and then 2537. I see. Okay, 0 to 9. So this has done some values there. What happened? I'm sorry, but I don't know what this means either. It's cheap to drive, digital display. Oh, look. I see. But why is B3? Okay. L1 has to be 1 here. L2 is to be 0. L3 is 1 and give us this value because L2, I think. Yeah, perfect. This is the first one. But how it goes to the first value, L1, it means that all these have to be zeros. Right? I don't know, I'm sorry about that. And now we have to implement L4, so I'm getting the implementation of the function for L4. Okay, now they're closed, we're going to 1 is true, switch is so, I'm going to 1 is 0, the false, switch is closed. I see. Switch representations. You have the examples of routing inputs through a maze, and some if conditions and the AND logic gate, and then this can be done with if, else if, else if, else. If, or, and not. It's like this, okay. So implementation of and or OR functions with switches and function series connection to true, or connection parallel connection to true. Representation of digital design, truth table, example, half headers, and then ladder. Oh yeah, I know. Yes, if you put the plus 1 give us 0 amount. This is the sum of the carry, yes. The carry out has 2 binary digits and with a 3. This means 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. Because it carries out. We have 3 ones. We have the presentation design, Boolean algebra, true and false, also 1 to 0, on and off. We have the variables ABC, XYZ, operates not and or, not X is written as X plus bar, X and Y is written X and Y, or sometimes X times Y, yeah. As we have learned this one, okay. X or Y is written X plus Y. Deriving Boolean equation or truth table. Yeah, this is a half header. 0 0 0 1 1 1 0 1 1 1 0 1. Don't forget, half header is only with 2 values A and B. With a full header is 3 values A, B, C. The representation of digital design, Boolean algebra, another example, ABC. I'm sorry about that, but carry in. Sin means carry in, code means carry out. Okay. Let's I see it. Sin in this case is done like cool way, look, no? Even while this is all 2011, this guy was pretty cool. Sin means input or output. Yeah, I know. And blah blah. Great representation of digital design, most likely use primitive building block in digital system design, standard logic gate representation, inverter, with a bubble. It's not. This is the it is called mainly and or. I don't know. It's kind of works like a knot, but I don't know yet. Representation of digital design gates. Okay. Waveform output. Okay, let's check this out because I'm pretty sure we tested that. Most likely use primitive building block in design, standard logic representation, blah blah blah. Fan in, number of input to the gate. Fan out, which means the number of gates. Inputs and output is connected to technology rules of composition, place limits of fan in, fan out. We have the waveform representation, dynamic behavior circuit. The relay circuits have non-zero delays. We have timing diagram of a half header. Output changes are delayed from input changes. The propagation delay is sensitive to path in the circuit. Outputs may temporarily change from correct value to the wrong value back again to the correct value. Is called glitch or hazard. I see. If you ever have a glitch there, it means the output has changed its values to the wrong value. But what was the value? Of course, we have binary digits, ones or zero. The block representation of the design, structure organization of design, black boxes with the input and output connections corresponds to well-defined functions and concentrates on how the components are composed by wiring. A full header is serialized in terms of composition of half-header blocks and block diagrams in full header. Okay, let's check the full header here. Yeah, this is realized in terms of composition of half-header. We have two input here, that HA, and one carry in at the HA input. Then it goes here with the sum output and the carry out output here with the OR is the OR with the bubble, I think. I don't know what the fuck that means. You have the block diagram section of ladder. The mentor CAD, a mentor graphic system has many companies use small partial tools, the Falcon design architect. That's great. I'm gonna use some programs for these cars. I'm gonna check that later, but because I cannot go through that because that's my Wi-Fi of the dorm doesn't allow me to go further than Google or YouTube. I cannot get any websites or download something from it. Okay. I see. Yeah, it seems pretty cool, to be honest. This is more like this PowerPoint now are just like for the programs of the mentor graphics. CAD. Oh, I'm gonna see this one. So let's say the summary. We've done the class demonstrations, the design tutorial, the design material. The next lecture is the memory elements. You have to read the fourth chapter. We are at the end. We finished with it. I hope I don't think I was clear at that, but I'm sorry. I'll do once again in the summer because I'm in school at the moment. It's winter here. I don't have time at all. I'm just doing these courses online just to be ahead on school. And then when I be in school, I want to be familiar with these terms and to know what I'm talking about and to know what the professor. If we don't have a female professor, not a professor. I don't know, who cares? Well, sorry about that one. Let's see. Yeah, don't forget if you wanna go further with it, the mentor graphics tool. I'm gonna check that out later myself. And I'm gonna update you as soon as possible. No problem. Down below the comments in the discussion tab, community tab. Even while you're still in a small community with 2 to 5 people, thank you guys. I really appreciate it, and I'm sorry for not taking things seriously on the online because believe me, I don't even have time to sleep at the moment. I sleep at 1 o'clock to 6. I wake up, do something like this online things, go to work, go to school, then go to work, 12 hours on work. Yeah, goddamn, 6 to 6, Jesus Christ. Anyway, guys, I'm sorry if you have any question or you think that I was incorrect or the PowerPoint was incorrect. Let me write it down below the comments so you can help each other there and you can grow a better community, a great community. Because I'm pretty sure that even while we're small community at the moment, like 2 to 5 people, in a few years it'd be awesome. I'm pretty sure about that because engineers are the best, homies, as I'll say. Just kidding. Okay, so we're at the end. So have a great time, guys. And if you have any question, or I was wrong, or PowerPoint was wrong, or any one of us was wrong, please write it down below the comments so other people can see and then can see the correct values. Okay, have a great time. Goodbye.